Thank you. So it's a pleasure to be here. And I thought, since I'm the last speaker, I thought we'd end with how the universe ends. Before we do that, let's see. These are my slides. We want to give you an introduction to cosmology and spend the first couple slides talking about, does that work? There we go. What we've learned in the past 2 decades. And I want to begin by giving you a sense of where we were when I was in graduate school and we learned about what the universe was like. The picture we had then was the universe was filled with matter, atoms like us, radiation, and that the basic picture we had was what's sometimes called and often called the Big Bang theory, but I think actually a better name for it is the expanding universe theory. The Big Bang theory was a name given by Hoyle, one of its detractors, and it misses the point, I think, which is the key picture to have is our universe is expanding. Our universe starts out very hot, very dense. As it expands, it cools. When it started out so hot and dense, it was a dense plasma of electrons and protons and radiation, so dense that all the radiation was trapped. About 380,000 years after the Big Bang, the electrons and protons combine to make hydrogen. At that point, the universe becomes cool enough that the radiation can propagate to us. And what we did with the WMAP satellite, one of the key pieces in answering the questions I want to talk about today, is we look at the microwave background, the leftover heat from the Big Bang. The picture that emerged from the WMAP observations, particularly from observations of supernova, subject of a previous breakthrough prize, but also our observations of large-scale structure, showed that the universe is expanding. Not only expanding, this rate of expansion is accelerating, and that the distance between galaxies is growing exponentially. We don't know what drives this expansion. We don't really know its future fate, and that's what we're going to be talking about as we go on. The observations also told us about the universe's beginning. To me, one of the most profound things we observe that tells us about the universe's beginning is we see fluctuations in the microwave sky. We look over there, and we look over there. We see 2 points in the sky that are coherent. Somehow information got from over there to over there. That doesn't sound too strange until you realize the universe is 13.8 billion years old. There's not enough time for the information to travel between 2 widely separated points. And in our standard cosmological picture, we didn't have a way of understanding how the universe could be so large, how it could be so uniform. The key idea that people have evoked to explain this is that the universe underwent an incredibly rapid period of expansion that we call inflation. And during this brief time, the size of the universe expanded by an enormous factor, and that's what we're trying to show in this figure here, that the radius of the universe expanded from 10 to the minus 40 centimeters to more than a centimeter in a trillionth of a trillionth of a trillionth of a second. And we think this rapid expansion that gave rise to much of what we see in the universe today. So this idea of inflation is the most popular idea we have about what went on. But tied into that, and the immediate question you ask was, what was there before? And broadly speaking, the ideas we have of what's happened earlier falls into 2 possibilities. One possibility is that time began with the Big Bang. There was no before the Big Bang, just like there's no north of the North Pole. That's as early as we can go. The other possibility is there was something before the Big Bang. And one possibility is that there was a big crunch, that the universe, instead of expanding in this pre-Big Bang time, was collapsing, somehow reached a maximum density, and then re-expanded. Third possibility, of course, is none of the above, that the universe emerged from some pre-Big Bang condition that we don't yet have a good description of. What's significant is these different possible stories make different predictions. And one of the important predictions of the inflationary universe, and this is something that Lyman Page talked about earlier, is gravitational waves. That there should be gravitational waves produced in the first moments of our universe's history during this period of rapid expansion. On the other hand, in this alternative cosmological model, there should not be gravitational waves. This is pretty cool. This means if we could go and see the gravitational waves, if we were to detect them, we would learn something about what happened in the very first moments of the universe. So far, things look pretty good for the inflationary model. One of the things we've seen in our observations are confirmation of some of its basic predictions, but we've not yet seen these gravitational waves, and that's going to be one of the big things in the coming decade. We're going to try to go out there and detect the signature of these gravitational waves in the microwave sky. Now, at this point, things get a little confusing, because you've probably heard about gravitational waves being detected. It was the subject of the Special Breakthrough Prize last year. And next week, our LIGO colleagues will get the Nobel Prize for their detection of gravitational waves. So why am I talking about looking for them? Well, there's really two different types of gravitational waves that we're interested in. And just like with observing electromagnetic waves, we're interested in seeing both radio waves and optical light and X-rays, and they're all telling us about different parts of the universe. We want to look at gravitational waves at different scales. The gravitational waves that we're seeing already come from the collisions of two black holes, and now the collisions of pairs of neutron stars. Their characteristic wavelength is kilometers, and they're already telling us a lot about these things like neutron star collisions. What we're going after is cosmic gravitational waves. These were produced in the first moments of the Big Bang. They're very long wavelength, the size of the visible universe. They've not yet been seen, though claims have been made and now, I think, discounted of these previous detections. Why do I care? Why do we want to see these things? This does not have practical impact. I mean, there's been some wonderful earlier talks about things that will prolong life and make our lives richer, healthier, perhaps save the planet. But here we're just trying to understand what's out there and get a glimpse into the first moments of the universe, understand physics at energy scales we have no other way of getting access to, and really just answer our curiosity about what happened in the past. As I mentioned, there's been claims to see this before. There was in the New York Times, not only did we see Putin invading Crimea, things that had impacts that still echo through today, kind of like gravitational waves telling us about our distant past. There was a claim that space-time ripples revealed the Big Bang smoking gun. We thought we saw gravitational waves. Now, what was going on there was, I think of this as I'm staring on the top floor of a high building in San Francisco, staring out, looking at, trying to see a beautiful sunset in the distance. I think I'm seeing something neat in the sunset. What I actually saw was smudge on the window. And when you look out, you really have to worry about what's on the window in front of you. For astronomers, the stuff that's on the window in front of us is stuff from our own galaxy. We're trying to look out 13.8 billion light years, and sometimes stuff that's a mere 100 or 1,000 light years away is this junk in our face. This junk turned out to be galactic dust, and that's why the signal went away. Intriguingly, this has not been the first time galactic dust has led us astray. In fact, much of cosmology could be viewed as dust confusing us. So what are we doing? We're now heading to Chile, where we're building a new experiment funded by the Simons Foundation. That's a joint collaboration between UC Berkeley, San Diego, Princeton, and Penn, combined with a number of other institutions throughout the world. And at this amazing site, incredibly dry, this is our existing telescope, we're building another set of telescopes to go after these microwave background radiation fluctuations. And here's the site from above, and you can see this is this incredible site to look out into space and look for the signature. These projects get to be big projects. This is just a list of the institutions that have come together to make this happen. We have over 160 researchers throughout the world working together on this project. And our hope, what we hope to, is to see these fluctuations. Will we see them? I don't know. That's why we do science. We don't know what the answer will be. We'll do the experiment. And if we were to see these gravitational waves, it would have a profound impact in our understanding of the universe's beginning. So now let me turn to the universe's end in the final moments of my talk. So we're seeing the fact that the universe is accelerating. It's really weird. That means there's energy associated with empty space that has the effects very similar to if I were to throw this thing up in the air, instead of coming down, it just kept accelerating and kept going faster and faster out into space. That's happening to the whole universe. The whole universe is accelerating, with this acceleration seemingly driven by energy associated with empty space. And while this sounds obscure, it turns out that our best understanding right now is 70% of the mass energy of the universe is in the form of energy in empty space. So we don't understand most of what's out there, and we'd like to figure out what's going on. We'd like to be able to answer questions about, is this energy changing with time? Is it constant, or is it associated with some field like the Higgs field that was recently detected and discovered? Will this acceleration end? I mean, there's a number of possible fates the universe might have. One fate is this acceleration will just continue. The universe will get colder and colder, emptier and emptier. It will be a universe that will someday end with a whimper. Another possibility is a more violent end. And in fact, there's some hint of this in the data, that the universe could be destroyed in a big rip, that the rate of acceleration will grow. Eventually, the acceleration will become so rapid that it will tear apart our galaxy, then tear apart stars, then tear apart the atoms that make us up, then tear apart the nuclei. That's called a big rip. I was actually asked about the big rip by a New Scientist early in November of 2016. My comment at the time was, to not get political, I referred to it as something that was physically possible and frightening to contemplate, like one of the potential outcomes of the election. So I'm now a big believer in the big rip, and fear that may be our fate a couple billion years into the future. So how are we going to go after this? Well, what we want to do is measure this rate of acceleration more accurately and see what's going on with the universe today. And the way we do this is studying two things about the properties of the universe. One is we measure the relationship between distance and redshift. We look at things that we know how bright they are. If I hold up a lamp, and you know how bright it is, you can figure out how far away it is. So we can measure distance with things like supernova explosions. We can also measure distance by measuring the size of objects. And we also look at how structure grows with time. General relativity tells us the relationship between the two. If we see a consistent answer that tells us general relativity is still working, we see a discrepancy, and a discrepancy we believe, and that's the most important thing, to have control of the systematics in our experiments so that we believe it, we might be seeing the breakdown of general relativity on the largest scales. The other thing we hope to learn is answers to the fate of the universe. by looking at the universe's basic properties. So in my final moments, I'll talk about what I've been spending a bunch of my time on. This is this project called WFIRST, the Wide Field Infrared Survey Telescope. My experience with this is similar to, I guess for those of you from Palo Alto, there used to be this sort of somewhat shady bunch of liquor stores as you head out to 280, the Gulch, where they now have a hotel we stay at. So you're in some shady part of town. Someone comes up and offers you a brand new stereo. They tell you it's completely legitimate, but they have no instructions. So I got this phone call about 5 years ago that said, NASA just got this new telescope. Don't ask any questions about it. It's really good. We got it from some friends. Had never been used. So it turns out that the Hubble telescope is one of only 17 telescopes that our country has built of that class. One points up, the others tend to point down. And one of these telescopes that was designed to point down was part of a program that got canceled, and they were going to destroy it. And then people involved realized this was potentially something very powerful for astronomy, turned it over to NASA, and I've been co-chair of the science team working to design the instruments that go on this telescope. The telescope's now sitting in Rochester, New York. It hadn't been moved. By building a very big camera, we'll be able to image lots of the sky. This telescope will be so powerful that every image it takes will have the resolution of Hubble, will be as sharp as the Hubble image, but it'll be 100 times the field of view. So you see 100 times more sky than the Hubble telescope does. So if you, as a result, instead of looking at these little tiny patches of the universe with Hubble, we will be able to survey much of the sky. And with that, we'll find lots of supernovae. We will measure distance. We will measure structure growth. We will see what the universe is doing. And 10 years from now, we will have a more accurate answer to what's going on with the universe's acceleration and what is its potential fate. So we'll see if the big rip's in our future. I'll leave you there. Thank you.
Thank you, David. Question up here in front.
What if our universe is a simulation?
What if our universe is a simulation? This is a question that I know it's popular here, but it's not a new idea. This really goes back to ideas people were asking philosophically for a very long time. How do we know that everything is not artificial? Everything is make-believe? That all the, we could imagine the whole universe came into being 5 minutes ago. All our memories are fake. I can't rule out that hypothesis, but as a scientist, that's not a very simple one. When I hear people talk about simulation, I'll now put on my hat as a director of a computational science center that we're building in New York. When you do a simulation, what you usually do is you coarse-grain things. What do we mean by that? If I'm looking at the flow of, say, modeling the Earth's atmosphere to do weather, I don't track each individual atom. What a simulation does is it represents things more coarsely. It says, this is the air temperature over San Francisco. My next cell in my simulation tells me the air temperature and properties, over Los Angeles, and I run a simulation that is a coarse-grained version of reality. And to say that something's a simulation means that it is representing a deeper reality with an approximate version of the equations. That doesn't seem to be how our universe is working. We have, remarkably, and this is one of the things we'll talk about the universe's simplicity, relatively simple equations seem to describe what's going on. So there seems to be no evidence for that hypothesis.
Question there.
Hi, thanks for the talk. I was wondering, why do we think that the big bounce model would not produce any gravitational waves at the beginning?
So the way you produce gravitational waves is you move mass around really quickly. That's how a black hole collisions produce gravitational waves. You've got all this mass spiraling around quickly. During inflation, the universe is accelerating very quickly. Remember that enormous growth in the size of the universe. One way to think about what's going on with inflation and why it generates fluctuations in gravitational waves is, I think, a lot like taking a pencil and balancing it on a point. And each point in the universe starts out as a pencil balanced on a point. And tiny fluctuations, even tiny quantum mechanical fluctuations, get amplified by the universe's expansion. And that part of space expanded for slightly longer, was these quantum fluctuations, than that part of space. And that makes the universe a little denser there, a little less dense there. The same thing happens with gravitational waves, roughly. You can think about this. The fact that you have these amplified quantum fluctuations means that you generate gravitational waves. During this collapse phase, the collapse phase happens relatively slowly on the scales we're interested in at the horizon size. So that when you generate density fluctuations that grow to form galaxies, you don't generate gravitational waves. That said, this theory is, at this point, incomplete. Some of you may have seen this New Yorker cartoon where the scientists are doing a calculation on the board. And there's a calculation, and there's a space, and it says, a miracle happens. And then the calculation continues. Right now, I'm safe to say this in Stanford. I can't really say this in Princeton. Eve is laughing in the front. She knows who I'm thinking about. We don't know how to go from the collapsing phase to the expanding phase. We just make some assumptions there. I think it's interesting to consider that model and assume that we don't generate fluctuations there. But the step we're missing is doing that. So given our current understanding of this bouncing model, we don't expect gravitational waves.
One more question.
Is it possible the expansion is actually a periodical process so that we can only understand the small portion of that?
So the question is the expansion a theoretical process?
No, periodical.
A periodic.
Also like four seasons, we can feel the change of four seasons, right? Because it's so short.
You
But
guys
for the
really,
universe-
okay, as someone from the Northeast, you do not really experience four seasons. If you are not shoveling snow, you have not experienced four seasons. But that's probably not what you were asking about. The question is, could we be living in a periodic universe? One that expands, reaches a maximum size, and collapses again. That doesn't seem, looking towards the future, that doesn't seem consistent with what we're seeing. We're not seeing the universe slowing down. So if the universe wanted to collapse, you need to expand, decelerate, reach a maximum size, and collapse again. That's not what our observations are showing. In fact, but what they're showing, and it's happening on a billions of years time scale, is the universe is accelerating. The dark energy is dominating. The universe looks like it's expanding forever. So it looks like the future, there's this wonderful poem, which I will misquote, about, some say the world will end in fire, others say in ice. A periodic universe, our universe ends in fire. It reaches a maximum density, collapses down again in a big crunch. What our observations have been showing us with the idea that the universe is accelerating, what we know about the geometry of the universe and its composition from the measurements we've made, suggests that our universe will end in ice, that will accelerate forever, end up emptier and emptier, and not be periodic.
Okay. At this point, I think time says we have to stop, and I'm going to turn this. Let's first of all thank all our speakers. Thank you, David. And the last word in this session belongs to Pete Warden.
Thank you. And David, I'd like to thank you. You know, I used to be involved with the dark side of the space program, and so trust me, the people that gave you that telescope, they're good people. They didn't steal it.
That's what I figure. They took good care of it.
They took good care. They built it with love.
Yes. Well, in fact,
And a lot of money.
And in fact, I think a lot of the people involved there want to make sure
Yep.
that it went to good use, and have been, well, I joke about that, they've been very supportive of making sure that this asset, which, you know, is built with a lot of our money,
Yep.
is put to good scientific use, and that's what we're trying to do.
Thanks.
Thanks.